Okay, in section 4, we are going to look at what is called the chain rule. And the chain rule is used when we have a composition of two functions. So a composition is essentially when you have a function that's not just x inside another function. So for example, we would use it in this first problem because you see there is a 4x plus 3, which is a different function inside of a squaring function. So the way I have it written here is if I let u equal 4x plus 3, then I essentially get the function u squared. Now, if I did stuff like we did before, if I just had y equals x squared, well, it's just an x. If there's just a variable inside your function, inside whatever it is, then you do not have to use the chain rule. But if there's anything besides just an x, then we have to use the chain rule. That's why everything we've done has only had an x. But you could certainly have lots of functions. I could have a trig function secant of 2x. Well, now it's not just secant x, there's something besides x in the function, so I have to use the chain rule. If there's ever anything in the function that's not just x or a single variable, then we have to use the chain rule. Now, the chain rule in itself is pretty straightforward. It says that the derivative of dy dx of a function u, u being the function inside the other function. So essentially, if we have some function in terms of x inside some function in terms of u, then all we have to do is take the derivative with respect to u times the derivative of the u function with respect to x. So up here we had this function 4x plus 3. Well, I picked u to be 4x plus 3, and then I had this function that's in u. So I could always plug this u back in and get my original function. But to take the derivative, it says first I want to take the derivative with u. So let's just say I was going to do the derivative of this one up above, this original problem. Well, the derivative of u squared with respect to u is just 2u times the derivative of the u function with respect to x. So we multiply by the derivative of the inside function, which in this case was 4x plus 3. And the derivative of 4x plus 3 is just 4. So that gives me 8u. Well, 8u doesn't look like the derivative of 4x plus 3 squared, but we know u is 4x plus 3. So we can replace that back into my function, and now this is my derivative. Now, that's kind of a complicated way to do it, and we'll do it one more time that way, but we'll see there actually is definitely an easier way to do that. Okay, so let's go ahead and look at one more. It's kind of broken down like this. It says find dy dx for the following: u squared plus 2, and u is 4x plus 5. So if I want to think of what this original function is, I could certainly think of that. The original function would have had to been y equals 4x plus 5 squared plus 2, because I'm just putting that 2 back in. So we recognize that there is some inside function u of this 4x plus 5. But if I want to take the derivative, if I want to find dy dx, I'll just take the derivative of the u function with respect to u, which is just 2u, because the 2 goes away, times the derivative of the u function. And the derivative of this is just simply 4. So that's 8u, but again, I can plug this u back in, and I can get this to be 8 times 4x plus 5. And if I wanted to distribute, it's 32x plus 40. Now, the problem with this method is you have to pick out what you have to kind of write it separately. I mean, it's not the worst thing in the world, but typically this is not how people take the derivative with the chain rule. They just kind of implicitly see there is an inside function and do that. So essentially, if we do it the shortcut way, what we're doing is we're taking the derivative of the outside function with respect to the inside times the derivative of the inside. And we'll look at a couple of these where we do this with this kind of like very informal rule as opposed to doing the u and all that. And we can check if it works both ways if we do it 2 different ways. Okay, so let's look at a couple functions. So this one you have to recognize that there is something inside the function that's just not x. So what we have is we have something in here to a fourth power. So if we consider this, what we have is we have something to the fourth power, and that something is x squared minus 4. So if I want to use the shortcut, what I'm going to do is I'm going to basically take the derivative of something to the fourth power. Something to the fourth power derivative will take the 4 down, and it'll be times whatever that is to the third power. That's fine. So that's the derivative of the inside. But the key is we keep the inside the same. So it's like we pretend the x squared minus 4 is just x. We take the 4 down, we take one less power. But now the key thing is we're going to multiply this by the derivative of the inside. And the derivative of x squared minus 4 is simply 2x. So the key thing is the inside doesn't change. We take the derivative with respect to the inside. So you see how this didn't change? But then we multiply it the outside, the derivative of that to the outside. That's the big difference. And then if I simplify this, dy dx is 8x times x squared minus 4 cubed. Okay, so if we look at this next one, now this next one is pretty awful because I'm going to rewrite it. It's going to be 2x plus 5, 2x plus 5 over x plus 4 to the 1/2. So my outside function is something to the 1/2. So if I take the derivative of this, if I take dy dx, the first part is really straightforward. I take the half down. Now it's to the negative half because I subtract 1. And the stuff inside still stays the same. So this still is 2x plus 5 times x plus 4. But here's why this one is awful. I now have to take the derivative of the inside. And I'm just going to write it like this. 2x plus 5 over x plus 4 prime. But the problem with this, the inside is now a quotient. So since the inside's a quotient, I now have to use the quotient rule, which is f prime g plus g prime f over g squared. So I have to do all that to find the derivative of the outside. So when your inside is a quotient or a product, you then have to go and use that rule. So we get all these rules that start to combine with one another. So we get 1/2 2x plus 5 over x plus 4 to the minus half. And I'll show you a quick way you can get rid of the minus half here in a second. And now the derivative of this is going to be the derivative of the top, because remember we're going to say the top is f and the bottom is g. So the derivative of the top is just going to be 2 times the bottom function x plus 4. And I totally messed this up. It is a minus sign for the quotient rule, not a plus sign. So I wrote that wrong. It's f prime g minus g prime f over g squared. I apologize for that. Minus g prime, the derivative of the bottom is just 1, times the top, which is 2x plus 5, all over g squared, which is x plus 4 squared. So now this is actually the derivative. We have done all the calculus. Now we just have to simplify this monster. So one thing you can do, instead of flipping the whole fraction, I'm just going to make it the reciprocal. So if I flip the fraction like this, then I can get rid of the negative exponent, just make it positive half. It's the same as making it 1 divided by. Flipping it is the same as just doing 1 divided by a fraction. And now this in here is going to be 2x plus 8 minus 2x minus 5 all over x plus 4 squared. And you could try to simplify this more, but I'm going to stop here. I mean, I'll, of course, simplify that numerator, but I'm going to just stop at 1/2 x plus 4 over 2x plus 5 to the 1/2, and this is going to be 3 over x plus 4 squared. So you can see with this chain rule, you not only get the problem where you have to multiply by the inside function, but when that inside function is a quotient or a product, you then have to use that rule as well. So it can certainly make some of these problems a little more lengthy. Now, these same rules can work for transcendental functions. So we just have to remember what some of our inside and outside functions are, and then know kind of our derivative rules that we learned for the trig functions in the previous section. So in this case, instead of having sine of x, I have sine of cosine x. So I have my inside function here. So if I think of what my function is, it's y equals sine of some other function. So to find the derivative of this, so the derivative of sine, remember, is cosine. So it's cosine of something. But remember, that inside doesn't change. It starts as cosine. It would still be cosine. So our derivative is cosine of cosine x times the derivative of the inside. Remember, the last step is always to multiply the derivative of whatever that inside function is. And so the derivative of cosine is negative sine x. I don't love how that looks, so how I would probably write it is I would write it as negative sine x times cosine x. It just looks a little cleaner, I think, if you write it that way. But you can see you should always have whatever was inside still needs to be there all the way through. You're just taking the derivative of that later on, but that should still always be there. And that's where people typically make a mistake. They'll change what that original inside function is, and you shouldn't do that. Okay, in this one we have h of theta equals secant squared. This one's kind of hard to see what the inside and the outside function is as it's written, because the inside function is actually secant, because h of theta, when I see secant squared of theta, that really means I'm taking secant on the inside and the whole thing is squared. So the inside is actually secant and the outside is the squaring function. So if you think of what your outside function is, it's basically something to the second power. So when I take the derivative, I'm going to take the 2 down. It's just a power function. It's 2 times something to the first. And remember, whatever that something is going to be the same, so it still has to be secant theta, times whatever the derivative of secant theta is, whatever the derivative of that inside function is. And the derivative of secant is secant theta tangent theta. Hopefully you've had a second to kind of write down a lot of those trigonometric derivatives, have that kind of somewhere on a sheet or something you refer back to. So h prime of theta is going to be 2 secant squared theta tangent theta. Now, the only reason it's squared is because I have a secant to the first here and a secant to the first here. It's not because the original was secant squared, it just happens to work out that way in this case. So h prime of theta is 2 secant squared theta tangent theta. But again, you notice how I took the derivative of that outside function with respect to the inside function times the derivative of that inside function. This will be a common theme. Okay, so today we're also going to look at a derivative of a new function, and that is namely the derivative of the natural log function. So the derivative of the natural log function, we say the derivative of ln absolute value x is 1 over x. And we do always like in calculus, we love when it's the natural log ln. Log, which is the common log, that's base 10, we don't like that as much. It doesn't have quite as nice of derivative. So if we have a log of a different base, like 10 or 9 or 8, we typically will turn it into a natural log. So if you remember that formula, log base b of a is ln of a divided by ln of b. So if we ever do encounter that, we'll go back to one of those algebra principles like this, but we can turn any log into a natural log. So even though we're doing all our work with natural logs today, it doesn't mean we can't do a common log, a log base 2, a log base whatever. We're just doing things in terms of natural logs, so it typically works a little nicer. So the derivative of a natural log function is simply 1 over x, for x not equal to 0. So we typically like to think about it as x being positive, because remember, we want the x to always be positive in a log function. So the derivative of that is always 1 over x. So if we look at a couple simple derivatives with that before we start using chain and all that kind of good stuff. So if I look at dy dx of 4 log x, well, that's going to be 4 times 1 over x, because the 4 is just a constant, and the derivative of ln x is going to be 1 over x. So that's going to be 4 over x. If we look at this one, f prime of x, we have 1/2, because that's just some constant out front, times the derivative of ln x, which is 1 over x. So we get 1 over 2x. So a log function, its derivative is pretty simple. It's just 1 over x. Or if you think about it in terms of the chain rule, it's 1 whatever is inside the log function. So as far as our functions, some of those trig ones were pretty nasty. This is actually a pretty nice one. So if we want to use the derivative of a log with the chain rule, we can actually use this principle. Well, the derivative of a log with something in it is just going to be 1 over whatever's inside the log times the derivative of what's inside the log. This is essentially the chain rule. It's the same thing. It's 1 over whatever your inner function is times the derivative of that inner function. Now, why we really like logs so much is we have a couple properties as well, if you remember from algebra, and here is our best property. If you remember, if we have log of x to the n, you can actually bring that n out front. That's a really, really nice property. There are some other properties that we'll write here that we'll probably use at some point along the way. If we add two logs together, remember I can write that as a log of their product, or vice versa. It works both ways. And if I have a log of two things subtracted, I can write that as the log of those two things divided. And that again works both ways. So those are three nice properties of logs. So whenever we have a log function, we really do like it. Now in this first derivative, none of these properties really help me because I have log of just something in there. I don't have a product or a quotient, so I can't break it apart or anything. So I'm just going to take the derivative. Now, we do have an inside, so it's really important to recognize that you have an inside function. The outside function is just ln of some stuff, and the derivative of log, remember, is 1 over x, or 1 over whatever it is. And so in this case, it's 2x cubed plus 3x. So it's 1 over the function inside times the derivative of that inside function, which is going to be 6x squared plus 3. Just using our basic, power rules. So if I multiply that, this becomes 6x squared plus 3 over 2x cubed plus 3x. Kind of an amazing fact that a function with a log, when you take its derivative, just becomes basically a rational equation with a rational expression with x's and things on top and bottom, but there's no logs or any of the transcendental workers anymore. So that's kind of makes log a unique function. Now this one is kind of a real mess if you look at it, because we not only have the log of x squared minus 4, but it's also squared on itself. So this would actually be really, really messy if we try to do the chain rule directly. It would actually be a double chain rule, because we have the square and we have the ln and we have the inside. But this is where that one of those properties I told you about previous is really nice, because I can just take this 2, that's an exponent of the log, and I can just write it out front. So now it's not a big deal. It doesn't really affect the derivative too much. So that is a really nice tool. That's why those properties, that's why I took those time to write those down, because they will come into play. So if we look at this one, so my function now, if I think about it, it is a chain rule because it's 2 ln of something. So the derivative is going to be 2 times 1 over that something, because again, derivative log is 1 over. We know that something has to be x squared minus 4 because that has to carry through, times the derivative of that something. And the derivative of x squared minus 4 is 2x. So with that property, it actually made this not so bad. If I tried to do it without using that property, this would have been a mess. So I get y prime is going to be 4x over x squared minus 4. Okay, our last function we want to look at is when we have an exponential with the chain rule. So if you remember, the derivative of the exponential function e to the x is still e to the x, which makes it really nice. So if we want to use it with the chain rule, the derivative of e to any power is e to that same power, because the inside doesn't change, times the derivative of that inside. So same kind of thing we've been doing, it's just using the exponential. So we did the trig, we learned the log, and now we're doing exponential, along with all our polynomial stuff. We kind of get this pattern where we learn these same things about these same sets of functions over and over and over again. So if we look at this one, so there is an inside, so our outside function is essentially 2/3 e to the something. So the derivative of e to anything is going to be 2/3 e to that same something, so that doesn't change, just like all these. But now we have to multiply it by the derivative of that inside. So I have to multiply it by the derivative of cosecant. And the derivative of cosecant, if you recall, is negative cosecant x cotangent x. I don't love the way this looks, so I'm going to clean it up a little bit. I'm going to put the negative sign out front. And I'm going to put my trig functions out front too. I mean, this is not a requirement. I just think it looks better like this. But if you write it a different way that is acceptable, obviously that's fine. Now, Delta Math and some of your other computer programs might not like it as much. But so just be careful the way you write it in those. All right, let's look at one more function. We have y equals e to the 2x to the 4th minus 5x squared. So again, we have y equals e to some stuff. So the derivative of e to the stuff is going to be e to that same stuff, right? That's not going to change. 2x to the 4th minus 5x squared, because the derivative of e doesn't change. But then we're going to multiply it by the derivative of that inside stuff, which is 8x cubed minus 10x. So dy dx is going to be, I'm going to write it a little different. I'm going to write it 8x cubed minus 10x times e to the 2x to the 4th minus 5x squared. Again, I think it just looks a little better that way, but there's lots of ways to write it. So that's a little bit about the chain rule. The big thing to look about this when you're looking for something that has the chain rule, is there a function on the inside? If there is, you're going to have to multiply that one extra step by multiplying by the derivative of that inside, as well as taking the derivative of the outside function with respect to the inside function. The good news is this does kind of complete our set of derivatives. We're going to learn some other ways to do some different derivatives. There's one more set of functions we have to do for derivatives, which is the arc trig functions, inverse cosine, inverse sine. But besides that, we really can take the derivative of almost any elementary function right now. So we'll obviously practice a lot of those, get some experience kind of combining some of these rules we've learned in these last 3 sections. So that's all for the chain rule. Obviously, if you do have questions, let me know. And we'll go over more of these, obviously, in the future.